So here it looks like we've got two objects, 2 kilograms of solid gold, and we know the starting temperature, and also 1.5 kilograms of liquid gold. So let me mark those off to start with. We have a block of solid gold, 2 kilograms of solid gold at initial temperature of 1000 Kelvin. And we also have a blob of 1.5 kilograms of liquid gold at an initial temperature of 1336 Kelvin. So just some blob of liquid gold. Five kilograms of liquid gold at an initial temperature of 1336. So we know everything we need to know about the starting situation. And we want to know when we put these together, what's going to happen. One thing I would advise in a case like this, since we're dealing with a blob of liquid gold, also what's going to happen to that liquid gold? What would you expect to happen here, conceptually? Cools in what way? Physically, what would you notice happening to the liquid gold? Yeah, it's going to start to solidify. Yeah, losing bond energy. Because the important thing is, it doesn't specify this in the problem, but you can look this up on the data table. 1336 Kelvin is the phase change point. It's the melting point of gold. So if it's already at 1336 and it loses energy, it's going to start solidifying. It's not going to change temperature yet. Because if you take a look at the three-phase diagram for this substance, make those straight lines. 1336 is the phase change temperature. So our energy interaction diagram is going to look something like this. And strictly speaking, we should be drawing a separate one of these for each object. But the liquid gold starts off all liquid, but just barely liquid. It's at 1336 in the liquid phase. So if it loses energy, it's going to be solidifying. The big question is, we don't know if it partly solidifies or completely solidifies, or if it completely solidifies and continues losing more energy, what's going to happen? What happens to the liquid if it completely solidifies and then keeps losing more energy? Yeah, it's going to lose thermal energy, which means it decreases temperature. So we don't know which one of those happens. We don't know, does this completely solidify or only partly solidify or completely solidify and get colder? So that's what we're going to need to figure out. Meanwhile, what's happening to the solid gold? The solid gold, yeah, it's going to gain thermal energy. So that means it's going to get hotter. It increases its temperature. What's the hottest the solid gold could get here? Right. Possibly as hot as 1336 Kelvin. In fact, if that happens, if the solid gold reaches 1336 Kelvin, what happens next? It would melt if it reaches 1336 and continues gaining energy. But in this case, if it reaches 1336 Kelvin, that's the same temperature as the liquid gold. And what happens if two objects are already at the same temperature? Yeah, if they're at the same temperature, that would be thermal equilibrium. And that might end up being in a mixed phase if there's still some liquid left. But the idea is if the solid gold reaches the same temperature as the liquid gold, then that's thermal equilibrium, which means there's no further heat transfer, which means that this gold cannot melt. Because the only way to melt something is to raise it to its melting point and continue adding more energy. In this case, as soon as the solid gold reaches its melting point, it's now at thermal equilibrium with the liquid gold, which means there's going to be no further heat transfer. The solid gold won't gain more energy. If it was in contact with something hotter than 1336, like let's say this solid gold was in contact with something at, let's say 1340 Kelvin, that's hot enough to warm it up to the melting point and continue adding more heat. So in that case, the solid gold might melt. But if the solid gold is only in contact with something at the melting point temperature, then the solid gold cannot melt because it's not going to gain any more energy after it reaches 1336. In fact, it might not even get that far. Maybe the liquid gold completely solidifies and starts cooling down, and they meet somewhere in the middle at a colder temperature than 1336. Of course, it's got to be above 1000 because the solid gold is warming up. So even without running any number crunching here, we can at least put some boundaries on what's possible. The liquid gold might completely solidify, might get as cold as almost all the way down to 1000 Kelvin, but we at least know it's not going to get colder than that. Meanwhile, the solid gold might get as hot as 1336 Kelvin or might end up slightly colder, but it's not going to get hotter than 1336 and it's not going to melt because it can't gain more energy after it's reached thermal equilibrium. Any questions on that so far? And before we get started on running the actual equations to figure out what really does happen, one thing I'd recommend in cases like this, if you're dealing with multiple objects, especially if you're dealing with multiple objects of the same element or same chemical, like these are both gold, it's a good idea to label those in some other means. Because if we talk about the liquid gold and the solid gold, that's fine. But once the liquid gold starts to solidify, it gets really confusing to talk about the originally solid gold and the gold that was liquid but is now solid. So let's label these. Let's call the blob of originally liquid gold, let's call that object A. And the original block of solid gold, let's call that object B. Just so we can refer to them without any ambiguity. So when we talk about object A, we mean this original blob of liquid gold, which might solidify at some point. And we're talking about object B, that means the original block of solid gold. Any questions on that setup so far? So it looks like the big question here, the big unknown, before we even start running equations, we don't know if the liquid gold completely solidifies or not. And we don't know if the solid gold reaches 1336 or not. And which one gets there first is really the important thing. Because what's going to happen if the solid gold gets all the way to 1336 first, what happens? Yeah, we're going to end up in a mixed phase. If the solid gold warms up all the way to 1336 Kelvin first, then that means the liquid is still in the process of solidifying. I should actually use the terminology I've already set up. If B warms up all the way to 1336 Kelvin first, then A doesn't finish solidifying. Or if A completely solidifies first, then what's going to happen? If A completely solidifies while B is still in the process of warming up, what's going to happen next? Yeah, it's all solidified, and that's going to get colder, which means they're going to meet somewhere in the middle. So the final temperature will be lower than 1336. So the final temperature will be less than 1336 Kelvin. So these are the two big what ifs we need to consider. Does B warm up all the way to 1336 first, or does A completely solidify first? So let's check both of those hypotheticals. What if B warms up to 1336 Kelvin? Or what if A completely solidifies? And to check both of those, we can analyze how much energy each one of those is going to take. For example, if B is warming up, what type of energy does that involve? Yeah, that'll be thermal energy. And what formula could we use for that? What's our usual formula for thermal energy that would be applicable here? Yeah, MC delta T should work because mass is what we're dealing with. And we know the mass of object B is 2 kilograms. And where can we get specific heat? Yeah, we looked that up on the data table. So looking up gold on the data table, gold. Looks like the specific heat of gold is 0.126. So 0.126 kilojoules per kilogram Kelvin. And then delta temperature, how much are we assuming that B changes temperature? If we're assuming it warms up all the way to 1336 Kelvin, what would delta T equal? Yeah, if we're going from 1000 to 1336, and note that we don't know for sure that it does warm up to 1336. This is just a hypothetical. If it warms up all the way to 1336, then the change in temperature would be plus 336 Kelvin. So we multiply that out. 2 times 1.2 or 2 times 0.126 times 336, and that's about 84.7 kilojoules. So that's how much energy the object B has to gain in order to warm up all the way to 1336. Any questions on that so far? And what about object A? For object A to completely solidify, what type of energy is involved there? Yeah, delta E bond. And we can use, what's our usual formula for that? Yeah, delta M times delta H. That is how much of the mass changes phase times the latent heat of gold melting. And for delta M, we should use mass of the higher energy phase, which in this case is liquid. How much liquid do we start with, and how much liquid are we assuming we end with? In terms of mass? Yeah, we start with 1.5 kilograms of liquid, and we're assuming that we end with 0 kilograms of liquid. So final minus initial would be what value? Yeah, strictly speaking, we'll use negative 1.5 kilograms for the delta M here. And then delta H, we'll want to look that up on the data table as well. So delta H for gold melting, heat of melting, 62.8 kilojoules per kilogram. So we multiply those together and we get 90 something. Yeah, 94.2 or negative 94.2. So that's how much energy the object A, the liquid gold, would have to lose to completely solidify. So based on that information, which one of these processes finishes happening first? Yeah, B warming up. And how can we tell that finishes first? Yeah, it takes less energy. Because keep in mind, these are exchanging energy at equal rates. As B gains 84.7 kilojoules, which is enough to warm it up all the way, in the same amount of time, A loses 84.7 kilojoules, which is not enough to completely solidify. So that means B does warm up all the way to 1336. A is mostly solidified, but has not completely solidified yet. And in fact, we know that it doesn't finish solidifying at all, because at this point, what do you know about the temperatures of these two objects? If B has warmed up all the way to 1336 Kelvin, what have we just reached? Yeah, the temps are the same. The same temperature means thermal equilibrium. So there's no further heat transfer. A has partly solidified. In fact, it has mostly solidified. I think we can now say that it is, since 84.7 is almost enough to completely solidify, but not quite. It has gone most of the way towards the solid phase, but not all the way there. But this is now at thermal equilibrium. There's no further change, which means we know these are the only things that happen. B does warm up all the way to 1336. A mostly solidifies, but not quite. And now that we know that this is enough to reach thermal equilibrium, we can now actually set up the conservation of energy equation. Since the thermal energy of object B and the bond energy of object A are the only things that are changing. So let's set that up. We know delta E total has to equal, is this a closed system? Is it exchanging heat just A and B with each other, or is there anything else it's exchanging heat with? Yeah, it does say the solid and liquid are exchanging heat only with each other, so we can treat that as a closed system. So delta E total equals 0. We can expand that delta E total into delta E thermal for object B and delta E bond for object A. And for delta E thermal of object B, we could write out the formula MC delta T, but the thing is we already calculated that. We know that object B really does complete the 84.7 kilojoules. So we know that delta E thermal of object B is plus 84.7 kilojoules. Can we likewise replace delta E bond with negative 94.2 kilojoules? No, because that doesn't actually finish happening, right? So we can't use the negative 94.2 kilojoules. That does not actually finish happening. But we can still use delta M delta H. Delta M times delta H. And we can use the same value of delta H, 62.8 kilojoules per kilogram. Because it is still liquid gold solidifying. So at this point, what's our only unknown? Yeah, that delta M is the only unknown. So we can solve for that algebraically. Subtract 84.7 kilojoules from both sides. And then divide both sides by the 62.8. And we get delta M equals negative 84.7 divided by 62.8. And it's about negative 1.35. Also, what would the units be here? Yeah, because the kilojoules and kilojoules cancel out. We're left with 1 over kilograms. So they take the reciprocal and we just get kilograms. So that means delta M is negative 1.35 kilograms. What does the negative signify here? Yeah, we're losing mass of liquid because the M, the indicator here is mass of the higher energy state, which is liquid. Delta M being negative means we have lost liquid. So the amount of liquid has decreased by 1.35 kilograms. 1.5 minus 1.35 is what, 0.15? So we're left with only 0.15 kilograms of liquid remaining. But what has happened to that 1.35 kilograms of liquid? Yeah, it's solidified. So the amount of the solid gold, the amount of solid has increased by 1.35. So we end up with 0.15 kilograms of liquid. 2 plus 1.35 would be 3.35 kilograms of solid. So we still have the same total amount of gold. We've just changed what phase parts of it are in. And the whole thing is now at what temperature? Yeah, the whole thing is at 1336 Kelvin, which is really the only reason why it can exist in this mixed phase at all. Any other questions on that?
I had a quick question. So for the E-bond energy, so it doesn't finish because it's a negative value, or?
It's more that it doesn't finish because there's not enough energy transfer to do so. The positive and negative don't really matter here. We should expect these to be opposite signs anyway, because B is gaining energy and A is losing energy. The important thing about these values is, if you think of them as absolute values, which one is a larger amount of energy?
For A.
Yeah, A requires a larger transfer of energy for this process to happen. But again, they're exchanging energy at equal rates. Like A loses 10 joules while B gains 10 joules. A loses another 10 joules while B gains another 10 joules, and so on. So if B has to gain 84.7 kilojoules In that same amount of time, A is losing 84.7 kilojoules, which is not enough to complete the change, because it would need to lose 94.2 kilojoules to complete the change. So generally, in a case like this, whichever process involves a smaller transfer of energy in terms of absolute value is going to finish first, because that's not enough to complete the other change, but it is enough to complete this change.
Okay, that makes more sense now. Thank you.
Mm-hmm. And I usually think of this as sort of a racing towards equilibrium sort of thing, that you got a hot object and a cold object, that one of them is gaining energy, and the other one's losing energy until they meet somewhere in the middle at some final same equilibrium temperature. So it's useful to set up these hypotheticals, figure out for each object, what's the next important critical temperature or critical change, and ask yourself, how much energy would it take to get that object to the next important change point? And how much energy does it take for the other object to get to the next important critical point like that? And then just keep going one step at a time. And it may take several steps until they meet in the middle. Like in some cases, there might be several phase changes involved. So it might take more steps than this, but the general process is the same. Compare one step at a time until they meet at some final temperature somewhere in between. Any other questions on that one? Or any other questions on the conservation of energy stuff in general? And if you want some more practice on this, if you go to my website, http://math.nshes.org/P7A, there should be a conservation of energy worksheet there with some more practice problems that emphasize this multi-step race to equilibrium approach. So give those a try. They should have solutions as well if you need a hint, and see what you can do with that. And you're welcome to bring those into office hours if you need any help with that. Let's take a look into the idea of conservation or mechanical energy then, the kinetic and potential stuff. Interrupt this one. So let's start with this idea of potential energy. What do you know about potential energy so far? Gravitational potential energy, yeah. In the sense of, well, what's the indicator for gravitational potential energy? Like, what would you have to do to an object to give it more gravitational potential energy? Yeah, increasing the height. So let's say, for instance, you have and spring potential energy. Yeah, we'll have to get to that as well. But let's start with gravitational potential energy. Let's say you have a cliff or a shelf or something. And you have a box. So let's say you've got this box with mass m, and you want to lift it up. So you want to put it on top of the shelf. So let's say this is the initial situation, and then the final situation is the mass is higher up. What's going to determine how difficult it is to accomplish that? Yeah, how strong the force of gravity is. Because if you take a look at this object in isolation, you just got this object, this box with mass m. That's constantly experiencing a force of gravity just by virtue of the fact that it's on a planet. So you've got a gravitational force. And what determines how strong the force of gravity is? Yeah, the mass of the object. In fact, the force of gravity is mass of the object times another quantity. Have you seen the idea of how mass and force are related to each other? This is something that usually isn't really covered in 7A and it doesn't really get seen much until 7B. But I think it's going to help understand how forces and energy fit together much more easily. If you have some object and you apply a force to it, what happens to that object? Like if you just got some moving object and you push on it. Yeah, it's going to cause it to accelerate. You've got some object in the process of moving, you push on it, you're applying a force, maybe you make it move faster. Or if it's moving and you push in the other direction, you're going to make it slow down. Or you could even make it change what course it's taking, change the direction of travel. But all of those count as acceleration. They count as the rate of change in velocity. So in general, if you're looking at a force on a moving object, or even if it's not moving yet, your force is going to make it accelerate and start moving. Force causes acceleration. But what determines how difficult it is to accelerate? Like you wouldn't have to apply the same force to everything to get it to accelerate the same rate. What else plays a role there? What determines how difficult it is to change an object's velocity? Well, friction actually counts as another force. So if there's friction, that's part of the force acting on the object. But let's say the object is totally isolated, it's just floating in the vacuum of space, and you apply a force to it. So no friction, no air resistance, there's just the force you're applying. What properties of the object determine how difficult it is to accelerate? Like if you just got two objects floating in space and you push both of them with the same strength, are they going to accelerate at the same rate? Assume no friction, no air resistance, it's just floating in the vacuum of space. And let's assume you push on them both with the same strength. Would they both accelerate at the same rate? Density is kind of related, but it doesn't actually matter how dense they are. What just matters is the mass itself. Like if you've got let's say a 1 kilogram block of iron and a 10 kilogram block of iron, if you tap them both with the same strength, the 10 kilogram block of iron is only going to accelerate a little bit. The 1 kilogram block of iron is going to accelerate more. In fact, it'll accelerate 10 times as much. In general, the relationship here is force equals mass times acceleration. That is, the more massive the object is, the more force it takes to get it to accelerate at a certain rate. Or to put it another way, more massive means the same force produces less acceleration. Like you could see this if you have, let's say, you've got a model train on model train tracks and an actual full-size train on train tracks. If you push on both of them, if you want them both to accelerate at a certain rate, you've got to push much harder on the full-size train than on the model train. Not because of friction or air resistance or what material it's made of, but simply because the full-size train is more massive. If it's 1,000,000 times more massive, it's going to take 1,000,000 times as much force to get the same result. So in general, force equals mass times acceleration, in the sense that applying a force to an object makes it accelerate, assuming that's the only force acting on it. But the more massive the object is, the more force you need to get the same acceleration. In the case of an object experiencing a force due to gravity, the important thing about gravity is that it follows a certain amount of acceleration. If you just have an object and you let it fall, it doesn't fall at a constant speed. It gets faster and faster and faster. So there's a certain rate of acceleration associated with Earth's gravity. And that acceleration is usually called g. On Earth, that's about 9.8 meters per second squared, or we often round that off to about 10 meters per second squared. Formally, I think it's more like 9.81, maybe 9.82. But if you just need a quick estimate, you can usually round that off to about 10 meters per second squared. That represents how quickly an object gets faster as it falls. So every second, the object is 9.81 meters per second faster than it was a second ago. That's the acceleration. And to calculate how strong the force of gravity on an object is, that is the weight of the object, you can multiply mass times acceleration. The mass of the object times the acceleration that would be caused by gravity if it were in free fall, those multiplied together tell you the force of gravity on the object. For example, let's say you have an object that is 5 kilograms, a 5 kilogram mass object. How would you calculate or what would be the force of gravity on that object? If you actually multiply those together, the mass of the object times the acceleration of Earth's gravity, what do you get? Yeah, about 50. And the units there, we've got kilograms from the mass times meters per second squared from the acceleration. And that's abbreviated as newtons. So newtons is the unit of force. Newtons means kilograms times meters per second squared. So 50 newtons approximately, I think more like about 49, is going to be the weight, that is the force of gravity of this 5 kilogram object. So the mass is how much, I guess you could say how much stuff it has in it, or how much resistance it has to acceleration. Whereas the weight is the force of gravity, how strong Earth's gravity is pulling on the object. Those are related by the equation force equals mass times gravity, but they're not exactly the same thing. For example, if you take this object to a different planet, its mass will still be the same, but it will have a different weight because it's experiencing a different gravitational force. Any other questions on the force of gravity so far? So let's say this object is not in free fall. Let's say you're holding the object and you want to lift it up, or even just hold it still. What do you have to do with your hand to prevent the object from falling? Like if you're holding an object, why does gravity not make the object fall? What are you providing to counteract that force of gravity? Yeah, your hand is pushing upwards against gravity. So your hand is providing an upward force to counteract that. So on the force diagram, we would include an upward force caused by your hand. So the force of your hand, the applied force. And how strong would the force of your hand have to be to balance that out? Keep in mind, you don't really need to get this box going faster and faster or slower and slower. You just want to lift it at a steady rate. So how much force would you have to apply in order to make sure it doesn't fall? What should we expect? You got to apply the same 50 newtons, the same as the force of gravity. You've got to apply the same force, but in the opposite direction, just to balance that out. That way, what's the total force acting on the object? If you add together, forces have direction though. So we're adding m times g upwards plus m times g downwards. Yeah, the total would be 0 newtons of force. Force is what's called a vector quantity. Vector just means that direction matters. So 50 newtons upwards plus 50 newtons downwards is 0 newtons. The total force is 0, which means this object doesn't get faster or slower. It's just going to continue moving in the same direction at a constant rate. So in general, if you want to lift something at a constant rate, you just need to apply as much force with your hand or whatever you're applying it with to cancel out any other forces that are acting on it. So you're applying this force as the object moves. And if you're applying a force as an object moves, what do we call a force on a moving object? If you're applying a force to this object as it moves, what do we call that? Kinetic energy is what it has as it's moving, but yeah, what you're doing is work. Your work represents a force applied to a moving object. Specifically, work equals force times distance, usually written as F times delta X. In this case, we'll write this as delta Y because it is moving upwards. But work is a transfer of energy caused by a force applied to a moving object. So if we take the amount of force, which is mass times gravity, that's how much force you're applying, times the distance, how high you're lifting it, that tells you the amount of work done. And since you're applying the force, you're transferring energy to the object, what type of energy would you say you have just created? If you're just applying this force as the object moves some distance, you've lifted the object up. So you're storing energy in it. In fact, you could even get that energy back. If you knock this object off the shelf, it's going to fall, so you get that energy back. So what do we call energy that is stored? Yeah, this is what potential energy is all about. Potential energy is essentially work that has been stored up. You're doing work to lift the object, you put it on the shelf, now it still has all that energy that you gave it in the form of potential energy, stored energy associated with the position of the object, usually position relative to something else, in this case, the position relative to the planet itself. So the work you've just done is a change in potential energy. Specifically change in gravitational potential energy because gravity is the force you're acting against. In fact, every potential energy is associated with some sort of force. There's gravitational potential energy associated with the force of gravity. We're also going to look into spring potential energy associated with the force of a spring as it compresses and stretches. But every form of potential energy is associated with some kind of force. Not every force has a potential energy, only forces that allow you to store up the work. In this case, you lift the object, put it on a shelf, you have stored the work, you can get that energy back by dropping it again. With a spring, you compress the spring, you're doing work, and let's say you tie it off. You've got a compressed spring that has stored some energy. Cut the string and allow it to expand, you get that energy back. It can push on something else. An exception to that would be friction, for instance. If you push an object across a surface with lots of friction, You've done lots of work to move it, but then it's just going to stay still. You can't let go and let it snap back. So friction usually does not allow energy to be stored. There's no potential energy of friction. But any force that allows you to do work and save it, store it up for later use, there's a potential energy associated with that. And that potential energy can be found by calculating how much work was done to harvest it or to store it. So we can say the change in potential energy of gravity is mass times gravity times change in height. Or you can strip the delta off of it and say potential energy of gravity equals mass times gravity times height. But usually what we care most about is the change in height and the change in potential energy. So mass of the object times acceleration of gravity on Earth, 9.81 meters per second squared, times how much you're lifting the object from start to finish. That tells you how much potential energy has changed during that process, which among other things tells you how much work you would need to do to make that happen. Any other questions on potential energy so far? All right, let me know if you have any other questions, and I will see you next time. You're welcome.